in your device. So see here the different types of MOSFETs are shown here. The first one is a bulk MOSFET. Second one is a fully depleted SOI MOSFET. Second one is a fully depleted SOI MOSFET with a buried oxide layer. And last one is a double gate MOSFET. So I'm going to have a double gate MOSFET. This is going to be the last type. So different technologies where you can how the electric lines of force are going to be traveling inside the MOSFET that is shown here. First one is a bulk MOSFET. So bulk MOSFET means you take a bulk semiconductor. In that you are going to have source and drain, and you are going to have a gate. Above that you are going to have a bulk semiconductor. This is going to be a bulk MOSFET. Fully depleted SOI MOSFET, that is also shown here. You have a box structure, you have source, drain, and you have a gate, and this is fully depleted with buried oxide layer. So you have a ground plane and a box and then buried oxide layer, and then this layer thickness is very large here, but it is very small here. It is buried oxide layer. And finally you have a double gate MOSFET where you can see one gate is here, one gate is here, you have the source here, you have the drain here, and you have channel between the source and drain for the drain current to flow. So conventional MOSFET is first type. It is bulk MOSFET. So electric lines of force will pass through the depletion region with the junction. So if I'm going to, you can see the electric lines of force are inside the depletion region. If I'm going to reduce the channel length, I have to dope the channel region. So in very small devices, doping concentration becomes too high for proper device operation. So you have to heavily dope your region for making the device dimension very small. So conventional for this dimension, if I am doping his light, means if I'm going to reduce the size of the device to half, I'm making it exactly half of the size, then my doping has to be high. Then only you can support the device for a smaller operation at the same doping effect. That's what they're saying. In very small devices, the doping has to be very high. Whereas in normal devices, the doping becomes very low. So when you reduce your device size, the doping has to be larger and larger for proper device operation. So most of the field lines propagate through buried oxide layer before reaching the channel as shown in the second diagram. The second diagram is fully depleted SOI model where you can see the electric lines of force will be completely passing into the buried oxide layer, then entering your channel. So it is a fully depleted SOI device. The short channel effects can be reduced by using a thin buried oxide layer and an underlying ground plane. So if you are going to overcome the short channel effect, you can reduce the buried oxide layer thickness. You can use a very thin oxide layer so that the electric fields immediately after crossing the buried oxide layer will come into the channel very quickly. So the third type, you can see that I'm going to use a very thin oxide layer. So instead of the electric lines of force from source to drain, they become terminate on the buried ground plane instead of the channel region as shown. So most of the electric lines of force, they come out and they get buried in the oxide layer and they will never reach the channel. Okay, very few electric lines will reach the channel. And in last case, and this approach has a large capacitance. So you don't require a large capacitance because when the capacitance is going to be larger and larger, it has going to has its own problems. Okay, so I have to go for an efficient structure which is going to overcome all the effects of short channel. So I am going to go for a double gate device where both the gates are connected together. The electric lines of force from the source and drain underneath the device terminate on the gate and it will not reach the channel. So see here. So where whatever lines of force entering the buried oxide layer from the source or drain, they will get terminated inside your gate. They will not go and reach your channel. That is going to be the concept of double gate MOSFET. But in previous cases, you see the first case, the lines of force will enter your channel directly. Second case, they will enter the buried oxide layer and come out. Third case, they will go into the buried oxide layer and die out. Fourth case, they will go into the buried oxide layer and reach the second gate layer and they will not come into the channel. So those electric lines of force which are coming out from source and drain enter the buried oxide layer, and they will reach the second gate terminal. And if they reach the second gate terminal, they cannot escape and come out. So they will reach the gate terminal and stop. So only the field lines that propagate through the silicon film itself can enter the channel and degrade the short channel characteristics. So this can be minimized by reducing the silicon film thickness. So what they are saying is, if I am able to control the silicon dioxide layer thickness, I can achieve this property. So this operation of conventional MOSFET is limited to high frequencies by the high gate capacitance. We have seen this. So the high frequency operation is limited by CG. CG is the gate capacitance. To make this capacitance smaller and smaller, I'm going to use a metal plate for the gate. So if I'm going to use a metal plate, that is going to make my capacitance large, smaller and smaller. The silicon dioxide between the gate and channel is a dielectric layer. So the channel itself is considered as a conductor, and the combination of three form a capacitor. So you have one gate, you have a gate, you have silicon dioxide, and you have channel. So these three form a capacitor. That capacitance is going to be the gate capacitance CG. So if I can minimize the CG, I can use the device for a high frequency operation. In dual gate MOSFET, you have two gate terminals, whereas in conventional MOSFET, I have only one gate terminal. So why I am using two gate terminals? To reduce the overall gate capacitance at high frequency. So my problem is MOSFET at high frequency is not that much effective because the gate capacitance is going to be larger and larger. So if I want to reduce the gate capacitance, the only option is having one more gate terminal inside the device. The voltages at both the gate terminals will control the flow of current through the MOSFET. In conventional MOSFET, ID is controlled by VGS and VDS, but here ID is controlled by both the gate, the voltage applied across the gate terminals. So it is similar to four-terminal device, because MOSFET is a three-terminal device, gate, source, and drain. But here, dual gate MOSFETs are four-terminal device, so it is similar to a tetrode. Tetrode is a device which has four terminals, right? And when whatever the input you are going to give across the two gates, that is going to control the characteristics of your dual gate MOSFET. So any queries you have in dual gate MOSFET? So construction, other things are very, very big. So I don't want to start that in today's class. So today's class, we have seen about what is a Schottky barrier diode, what is a Schottky diode in general, and then we have started learning about what is dual gate MOSFET. Okay, so construction of dual gate MOSFET, how it is going to work, what is the equivalent circuit, what is the notation for dual gate MOSFET, all those things we will study once you come back after your CAT exams. So I hope I have put it in the WhatsApp group. The CAT exam portions are going to be, Unit 2 is going to be full, and Unit 3 except the last two topics, except FinFET and dual gate MOSFET. Actually, those two are present in Unit 3, but in the textbook it comes in Unit 4. So we are reading just now those two topics. So those two topics are not there. Apart from that, you have JFET and MOSFET fully from Unit 3, and Unit 2 is going to be completely there for your CAT exam. So do prepare well. I have uploaded the materials already in the Google Classroom page, and assignment and MCQs are also there. So you can refer to those questions also to see how questions can come in your CAT exams.